17th, 18th centuries, where people were examining physical universe much more carefully, and for example, questions about whether it was possible to consider empty space or not were being discussed. So the ancient Greeks had reservations about being able to treat empty space as something sort of independent of other stuff. But the 17th, 18th century scientists started investigating the possibility of thinking about space as being free from any stuff inside it, trying to create a vacuum, for example. And in the framework of Newton's laws, these are sort of operating in sort of empty space quite happily. But if we forward then again to 20th century physics, things become then again more complicated. And the confidence and certainty that the 19th century mathematicians had about the void or vacuum started going the other direction again. People started becoming more aware that this is still a rather problematic concept and actually full of subtlety. So modern 20th century physics treats the vacuum as a really central but very complicated and rich kind of concept. So to the modern physicist, the vacuum is full of possibilities. It's not at all just empty space and nothing in it. So this is largely due to the role of quantum mechanics and a certain principle called the uncertainty principle, which roughly tells us that we can't really know everything about a situation, let's say. And that goes for any kind of situation, even a situation where it looks like there might be nothing in it. So if you have a situation where you have some empty piece of space and there's nothing in it, you still can't know everything about it. And that can be interpreted as saying that there's the lowest possible energy sort of for empty space, but you can't really make that energy completely zero. There's always some energy there that's kind of a bottom possible energy, but that supports various strange things that might happen. So in the modern vacuum, physicists think that there's all these simultaneous creation and annihilations of particle and antiparticle pairs that are sort of instantaneously happening, where we will have a little bit of empty space, and suddenly there's an electron and a positron. So an electron has an anti-particle called a positron, and these things can be created sort of out of nothing, more or less, and then shortly thereafter they can then annihilate each other and go back to nothing. So that this quantum vacuum is sort of seething with all these possibilities of these particles emerging for a short period of time and so on. It's very rich and mysterious kind of concept. So the modern physicist now is returning to not being so sure what nothing means, actually, in the kind of physical kind of world. And so it's a very interesting story about nothing. I think the last word has not been said. And I would like to really emphasize the possibility that maybe even in mathematics, which is potentially independent of these quantum mysteries, even in mathematics there's the potential room for thinking about nothing or the void in a different or an additional way to what we already have. So I don't necessarily want to change the role of zero, which is great, a very important concept in our number system and so on. But I do want us to think more liberally about the possible role of nothing, a more fundamental kind of nothing than actually zero. So zero is still something that's been created out of nothing. But I want to propose that there's room in mathematics for nothing, which is still just nothing. Okay? It hasn't been converted into something. We don't have to create something from nothing. We can think about nothing itself. And that can be a concept that can help us. And so, okay, that's what I want to do. I want to introduce nothing into mathematics again, but in a more primitive, fundamental, really void kind of fashion. I think it's a role to play. And that's especially clear when we have this multi-set point of view that we're getting used to here. So in our next video, I want to talk about nothing in a multi-set context and why mathematics really does need new thinking about nothing. I hope you'll join me for that. I'm Noah Robiger. Thanks for listening. Today we are going to be looking at almost philosophical aspects of what is mathematics really about. It's a very interesting question. Of course, it touches base with philosophical or scientific issues, and there's lots of different opinions that are possible. But I'm going to be sort of positioning things in a somewhat novel way, as you'll see. There's a really essential dichotomy or duality which manifests itself. So if you'd ask the ancient Greeks about what mathematics was, they would have probably said something like arithmetic and geometry. So this is what we're talking about pure mathematics. Applied mathematics, of course, also involves astronomy and other subjects. But pure mathematics really rests on arithmetic and geometry, and later on algebra would also have been included in that general story. Now, which of these is actually fundamental has changed over the years, and with the Cartesian revolution, the emphasis has shifted from geometry being sort of fundamental to more arithmetic. And that's really what most mathematicians these days, I think, would lean towards, that arithmetic is really sort of a bottom of mathematics, really resting ultimately on the framework of the natural numbers, which were denoted by NAT for that. But in the 20th century, a new direction appeared. When people were trying to create a framework for modern analysis, they realized that things were a little bit difficult, and they ended up bringing in philosophers and philosophical approaches, which ultimately ended up in creating this set theory, this modern set theory, which ostensibly is some kind of framework for analysis. We are going to critique this very strongly in future videos. But that was sort of the motivation for this introduction of set theory as a sort of foundational framework for mathematics. And in that direction, people started asking, well, if we're going to use set theory to prop up analysis, they didn't say it that way, of course, but that was really what was going on, then how about other parts of mathematics? Can we build arithmetic from set theory? And then they did come up with a scheme for doing this. So by the end of the 20th century, we had this idea that first we start with set theory, and then we create arithmetic and geometry and algebra analysis and so on from that. And here is this way of constructing natural numbers from sets that goes back to John von Neumann, as we talked about. So in this framework, everything is a set, and the starting point is the empty set. That turns out to be what we equate with the number 0. And then we create the number 1 by taking this empty set and taking a set containing the empty set. So it's really the set containing 0. And then the number 2, well, one way of describing it is that it's the set consisting of both 0 and 1. So here is 0, and here is 1, and that combination is the number 2. And then the number 3 is the set consisting of 0, 1, and 2. So there's 0, there's 1, and there's the 2 that we just created. So we get this inductive way of creating natural numbers using these ever bigger zoos of force of sets within sets within sets. So if we ask something like, what is 78,143 explicitly in the system? Well, then we have a very big headache, and we have to actually stare at that thing. Write it down for a moment, stare at it, just in terms of these brackets. It would be a very big headache. But aside from being rather unwieldy, and I think to most people unnatural, this set theoretical approach to natural numbers also has some theoretical challenges. In particular, how are we going to define the operations of addition and multiplication on natural numbers when we view them in this very complicated set theoretical fashion? And then, how are we going to prove the laws of arithmetic from those definitions? Now, it is supposed by most practicing mathematicians that this has been done somewhere over the hill. Some logicians have done this, and we don't have to worry about it, that the laws of arithmetic are just God-given to us by the logicians. It's an unhappy state of affairs, so it means that modern students aren't actually exposed to seeing the arguments in front of them. We're not talking about something that's very tangential or oblique. This is a core issue in mathematics. How we're going to set up arithmetic with natural numbers. And if we're going to do it in such a convoluted way that we can only sort of point at these indirect references to things which are somewhere else, it's a very unhappy state of affairs. So the 20th century thinking has been very disappointing, really. There's this whole sequence of wrong thinkings that have been introduced in this general direction. We have this idea that math is based on sets, that everything is a set. The definition of set itself is finessed by the use of axioms. We really ought to define what a set is properly if we're going to base everything on sets. But that's too hard, and so we just assume that we know what a set is and invoke axioms to conjure up the things that really ought to be theorems. The foundations of arithmetic, then, become subservient to, well, unwieldy and overly complicated set theoretic arguments. The naturalness of arithmetic is lost. We're giving up our arithmetic to the set theorists. And in fact, no one really views the proofs critically. When I say no one, I mean practicing mathematicians, students at universities, people who actually then use these mathematics. To them, these proofs are essentially non-existent. They're invisible. It's a very unhappy state of affairs. We're talking about arithmetic after all. We ought to be able to lay out arithmetic in a more sensible and more publicly verifiable way than this. So I'm going to be advocating a very different approach to arithmetic and how we set up arithmetic. Very different from the 20th century's point of view. So the advantages with our approach to arithmetic is that, first of all, we are going to be flexible about which data structures are suitable. We don't just have sets at our disposal. We have lists, ordered sets, multi-sets, as well as sets. And we have now some experience being able to judge that maybe in certain situations one of these is better than another. So we have a flexibility that the set theorists don't. This gives us a big advantage. Our definitions are going to be clear, and they're going to relate directly to common usage and intuition. We want an ordinary person to be able to look at our definition and say, yeah, that kind of corresponds to the way we think about things. Especially when we're talking about natural numbers and their arithmetic, for heaven's sakes. The theoretical manifestation of the subject ought to correlate with the way people actually do arithmetic. That's not asking that much. Our proofs are going to make sense. They're going to be visible. We can actually explain them to non-experts. We don't have to pretend that we need all kinds of prior logical training in order to be able to deal with the complexity of these proofs. And we'll see that the doors are open to further insights into adjacent fields. Once we understand arithmetic in a better way, well, a lot of other adjacent things are just going to be more accessible to us. And we're going to fix reality, okay? And avoid wishful thinking. Just because we want something to be true doesn't mean that we're going to force it into our theory. We're going to let nature decide what is true. All right, so here's our main definition, key definition of what a natural number is. That a natural number is an M set, or multi-set, of marks. Marks on a page. So, for example, this thing here is an M set, as you can see by the brackets on the outside, and it contains a mark, and another mark, and another mark. So these vertical strokes, or marks, are going to be the things which are inside our M set. There's only going to be one kind of thing in these M sets. They're always going to be the same, these vertical strokes or marks. So that's what we ordinarily call the number 3. That's going to be our official designation, physical specification of what we informally call the number 3. The number 17, that's what it looks like officially. It's a multi-set consisting of a lot of strokes, and there's a stroke for a mark, mark there, mark, 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 mark. That's going to be our number 17. And, notably, we're going to allow, because we're talking about M sets, the possibility that there are no marks inside our M set, that it's an empty M set, and that's going to be our number 0. So, exactly, it's a mark. Okay, so it's something that we're writing down on the page. It's a symbol, and it looks kind of like a 1, but I try to make it a little bit longer than a 1, so that we distinguish it a little bit from the number 1. But what does it actually represent? So the answer involves going deeper. So I claim that the natural numbers are not at the bottom of things. That's usually the point of view towards modern mathematics. That there's actually something else underneath the natural numbers. And I'm now going to reveal what that is. There's something even more fundamental, essential, basic than our number system. All right, so what is this essential dichotomy or duality underlying mathematics? It's revealed here in this slide, which arguably might be the single most important slide in all of my videos. What do we see? Well, we see on this side, nothing. Nothing. On this side, something. There's a difference. The difference between nothing and something. I claim that this, simple-minded though it is really the essential core dichotomy or duality underlying mathematics. The distinction between nothing and something. So this mark or stroke that we're representing here, this basic symbol that we're using as the ingredients for our natural numbers, this is our representation of something. It's a symbol that we introduce which represents this intuitive idea of something. So we are definitely accessing our intuition here. We're not giving definitions of something or definitions of nothing. If we did that, we would go in philosophical circles. We could do that for years and years, talking about what does nothing mean, what does something mean. Okay? I just want to base things on our intuitive understanding of those terms. We all have intuitive understanding of those terms. And represent the something by this symbol. There are other possible symbols that we could have used and that we could use. So we've used this one here, but maybe somebody else might be more comfortable with a small circle, or a star, or maybe a slanted line, or maybe even a dot. Those would be alternative, completely valid ways of representing something. We could have other symbols as well. But the point is, we're just choosing one particular symbol, and that symbol represents this primordial idea of something. And nothing, well, there's no choice about how to represent that. There's a lot of choices about how to represent something, but there's no choice about how to represent nothing. It's always represented in the same way, by emptiness. You leave the page empty, you don't put anything in it. That is nothing, in our view. How we're representing nothing on the page. It's just empty. So although we use the general definition of natural numbers as M sets of marks, we still want to construct them. Okay? We want to create them, put them on page, demonstrate what it is that we're talking about explicitly. And we're going to do this inductively, which means one step at a time. And we're going to start with our empty M set, which is the simplest possible situation. It's the empty M set which has nothing inside it. It contains nothing. And we're going to give it a name. We're going to call it 0, because that's the traditional word that we use for that particular number. And we'll often write it as a separate symbol with this sort of alt-type number symbol. So 0 is, by definition for us, this M set here. So, in fact, this symbol here is extraneous. We don't actually really need it. It's logically unnecessary. We could use just this here instead of 0 everywhere, but we prefer to protect the ordinary experience and just then think about the usual 0 as being actually, officially, this empty M set. So for us, this is the first natural number. It's the first one that we actually explicitly write down. The first natural number is 0. And now we can construct more natural numbers. And the idea is always the same. We're going to take what we have and we're going to add something to it. We're going to insert something. So the next one is this one here, the set or M set consisting of something. It's a M set with a single mark in it. So make a mark, put it in an M set, and that we can say is the number 1. And then we can take this one and we can insert another mark beside it. So we have mark, mark. That M set is 2. Mark, mark, mark. That's the M set 3. Mark, 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 mark. That's the M set 4. Mark, 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 mark. That's the M set 5. Notice how, first of all, how much simpler this construction of natural numbers is than the set theoretical one. Notice that it's actually a natural progression that actually mirrors ordinary usage. Primitive peoples would have written number 5 in very much this way. A bunch of 5 marks on the page, piece of papyrus or something. This is very natural. The only thing that's a little bit sophisticated that they wouldn't have done is putting everything in a pair of brackets to enclose it, to make the boundary very clear that the natural number doesn't extend out here or out here. So these natural numbers are so constructed in order. We see that it's not just that we have a whole bunch of natural numbers. Rather that we start with 0 and then we start to sequentially construct more and more. There's a natural order. After 0, then we have this one, and 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 so on. And we can keep going. At least until our patience or our resources runs out. So this is very explicit, very concrete, and now there's no more question about whether we have a natural number or not. So from this point of view, you have a natural number precisely when you can actually write down a multi-set of marks. If you can do that, then that's a natural number. If you can't do it, well, then you don't have such a natural number. It's a very explicit way of pinning down arithmetic to something concrete and, in fact, very close to our experience. So this is going to, I think, be a good foundation for arithmetic. It's a very good foundation for arithmetic. But notice that it's exploiting our understanding of multisets. If we weren't comfortable or familiar with multisets, we might not think to do this. If we were only focused on sets, then we're not able to do this. This is something that we can do because we do understand multisets. A big power that we've gotten from understanding our data structures and not just sticking to 20th century set theory. Okay, so one key ingredient in this discussion is this role of nothing. Okay, identifying nothing as a kind of ingredient in the story. I think it's worthwhile for us to explore this a little bit more and to discuss other ways in which this nothing concept is going to figure in the mathematics that we're slowly going to create here. We've already seen some examples of it, but we need to readjust our thinking a little bit because the way we think about nothing currently in mathematics is subtly and quite distinctively different from what I'm advocating here. So we have to get on top of nothing. We'll do that in our next video. I'll do something for that. I'm Robert Robert. Thanks for listening. In today's video, we're going to move towards reconsidering natural numbers. This is, of course, a very fundamental part of mathematics, and it's actually how we started this series some years ago. But now with our investigation of really big numbers and really big arithmetic that goes with those big numbers, we've started to see that maybe there's room for consideration, again, of what a natural number actually is. So here are some questions that will motivate us. First of all, what exactly is a natural number? Can we say precisely, concretely, logically what a natural number is? Should we distinguish between different types of natural numbers? Maybe there's some reason for separating the different kinds of things that we've been currently grouping together in one big box into separate boxes and looking at things a little bit more finely. And should we distinguish between natural numbers and arithmetical expressions? Arithmetical expressions can evaluate the numbers, but there's some reason to believe that we should treat them as essentially something separate from the numbers that they evaluate to. So, in thinking about these questions, I think it's instructive to keep in mind the words of a very well-known American mathematician, Eric Bishop, lived from 1928 to 1983, who was a pioneer in what sometimes called constructive mathematics. We're going to be talking about his work, especially when we get to calculus and analysis more. So he is a very important thinker in the 20th century, one person who realized that the status quo really needed to be moved in a different direction. But he gave a very lovely prescription here, which I think is well worth studying. He says, meaningful distinctions need to be preserved. Meaningful distinctions need to be preserved. He's talking about a situation where you're looking at something and there's different kinds of objects and there's something fundamentally different about them. And what you don't want to do is just lump them together, ignoring those fundamental differences that are actually there. You must acknowledge those differences, those distinctions, and build them into your description of what's going on. Very sensible and very actually useful kind of dictum. So far in this course, we have treated natural numbers as belongs to one type called net. And this has included actually quite a few different kinds of objects. So we started out by thinking of the number as a rather primitive listing of marks or strokes on a page. That's going back to sort of Neanderthal arithmetic.